Right. Right. So, good. So, ready. All right, we are in time, so I'm thinking to finish this chapter today and start chapter 6. But if we cannot start chapter 6, that's okay. Yeah. So I'm trying to finish chapter 5, the thermodynamics. So uh, I told you in the last class, very important concept, but it's very simple, the first law of thermodynamics. And I told you in the homework and in the exam, you always get at least 1 or 2 questions in first law of thermodynamics. Yeah. So the statement is energy cannot be created, energy cannot be destroyed, energy is conserved. Yeah. So energy is converted from one form to another form. And whatever energy I get from somewhere, that much energy I spent on something. Yeah. So that equation was I write this equation, dt is equals to du plus dw. So this is so d is a small work. So d means when you go to the higher level course, it's a little bit complicated than this equation. So we just model this equation is a tiny bit, and we sum it to be a big work. Yeah, it's just like the calculus. So we write this d means very small amount. This d means very small amount work. Yeah. And this is d means very small amount change in internal energy, and this d means very small amount absorbs energy. Yeah, so something absorb the heat. So like that. So I told you, let's say you have a gas cylinder here, and you put in heater, and this gas absorbs 1,000 joule of energy. 1,000 joule of energy. So you are going to put 1,000 joule of energy. So in our case, in this course, we are not doing compression. I'm not doing this piston going down, so you don't have to worry about the sign convention in this class. Yeah. So we are just doing absorbing heat, and this piston is moving up. So it was here at the beginning, and so from here the piston absorbs 1,000 joule heat energy, and this piston is moved up a little bit like this. And so this amount, how much is this distance or the volume? So this is dV, and some pressure is pushing it from outside. That is P. That's a pressure. So if you multiply that pushing down pressure and this volume change, that comes to be PdV, and that amount is a work. So let's say, so this work is about 200 joule. So on pushing from here to here, the work we define that as a pressure multiplied by the dV. So let's say that is 200 joule. And so how much heat out of this 1,000 joule is used to increase the temperature of this gas is du. So it's pretty simple. Look here. So du would be, so you take this guy this way, and 1,000 minus 200 would be 800. So look here. So this is 1,000 joule, and this comes this way, 200 joule, and this is du. So out of this 1,000 joule, 800 joule, about 80% of the energy is used to, about 80% of this absorbed energy is used to increase the temperature of this gas, and about 20%, which is 200 joule, is used to push that piston off. So that 200 joule is a really important. 800 joule is a bad thing. So we don't, while we are working, we don't want our car engine to be too hot. We want the car engine to drive fast, far than to be hot. Everybody got that? So heat is not good in thermodynamics. This absorbed heat is good, but the heat produced, this du, is a bad thing in thermodynamics. This is what we are looking for. Got it? So if you calculate what is the efficiency of this engine, basically this is a heat engine. So 200 joule work is produced here out of 1,000 joule. 1,000 joule here, and you multiply by 100 to get percentage. So this comes to be about 20%. So a modern day car engine or aeroplane engine or any kind of engine you drive, they have 20% efficiency, maybe 20, 21, 22. Yeah. So if you burn let's say 100 liter of petrol, in your car, about 20 liter is only used for driving car, and all about 80 is gone for the heating that engine, and it just dissipated or the heat goes outside in the environment. Everyone got that? So this is the first law of thermodynamics. Good. So our car engine is about 20%. So that's this expansion. So I suggest to do this way. It's a much easier way. Yeah. So dq is always big number, and du and dw are just cutting this 1000 into small number. And always, if you look any thermodynamics book, this number is always smaller than this du, because most of the fuel we burn goes out in the environment as heat, and very tiny amount of the heat is used to drive the car. Everyone got that? So in future, if you take a engineering or other thermodynamics course, then there is a much more sophisticated explanation. So I just wanted to say that. Now, I'm in the second slide now. This is about state function. State function. So what is state function? So state function is no matter how you travel, you reach the same place. So that kind of property is called a state function. For example, let's say you have a gas here. So let's say this is a 1 liter gas here. You can expand this gas multiple ways. So maybe you want to expand this 1 liter gas from, let's say, 1 liter to 2 liter here, and then from 2 liter you may want to expand from, let's say, 5 liter here. So you go from 1 liter to 5 liter in 2 steps, right? Everybody got that? So first of all, you are in 1 liter, you pull this piston a little bit up, and you go to reach to the 2 liter, and then you further pull this piston up, and you reach to the 5 liter. Everybody got that? You could go this way, or you could go this way also. So you have 1 liter here. Now you directly push, so pull these pistons directly up in 1 step and reach to the 5 liter. You look here. So you started from 1 liter, you reach to 5 liter, right? Here also you reach to 1 liter, you reach to 5 liter. So here you are walking in multiple steps, but here you are walking directly in the single step. What is the volume change here? Look here, in the volume change, initial volume is 1, final volume is 5. So dV, the volume change, d means change in volume, would be 5 liter minus 1 liter is 4 liter. So look here, 5 liter minus 1 liter is also 4 liter. So no matter how you expand the gas, slowly, multiple steps, many time, or you single step, the change in volume is same, right? No matter which path you travel, you reach the same state. Everybody got that? So out of, let's say, it's very simple. If you think like, I have 105 students here, so only about 30 students come to class. There's 75 students study in home, right? But you come here and you pass. And those students who don't come to class, and they also pass. So they reach to the same state. So passing is a state function. Everybody got that? Whether you come to class or you study in home, you reach in the same state. If the change is same, you just pass, right? So passing is state. Everybody got that? So let's look. So the volume is state function. Now let's look another one. So volume is change in volume is state function. So let's look a temperature change. Let's say you have water here. So you already know how to measure the temperature of water in the lab. So put the thermometer here, and you have 21 degrees centigrade at the beginning. Now you put this in the oven, and you turn the oven very slowly, so a tiny bit, maybe about. So there are many steps in oven, right? Just to turn the oven. So turn the oven a tiny bit here, and it starts to take long time to boil this water, and this becomes, so here you have a 21 degrees centigrade, this thermometer showing. So you just turn a little bit oven here, and it boils to 100 degrees centigrade, and it might take 5 hours. 5 hours, it go from 21 to 100 degrees centigrade. Make sense? Why take 5 hours? Because you really supply the heat in tiny bit, right? Everyone got that? Or you could do another way. So you have a water at 21 degrees centigrade here, 21 degrees centigrade here. There is a thermometer. Now you put in the heater and really turn the heater very big on, right? Can you turn the heater up to 6, right? You go to home and look your oven. So there is a 1, 2, 3, 4, 5, 6 step, and 6 is the maximum in my home apartment. Yeah, just look at your oven. So turn the oven all the way to 6, and immediately within 2 minutes, you get 100 degrees centigrade here. Look here. So 21 to 100, 100 minus 21 is 79 degrees centigrade. Here also 100 minus 21 is 79 degrees centigrade. So here you are heating the water by giving a tiny bit of heat here, and it is being heated in 5 hours to reach from 21 to 100 degrees centigrade, and change in temperature is 79 degrees centigrade. Here you are really turning the heat a lot, and immediately within 2 minutes the water is boiling. 100 minus 21 is 79 degrees centigrade. So no matter how you heat the water, the change in temperature is same 79 degrees centigrade. Everybody got that? It's a state function. So now let's look the another one. And so change in that was a change in volume. The change in temperature, I showed you 79 degrees centigrade. So this is also a state function, right? Now let's look the pressure change. So here is a gas here. So here is a gas here, and here is a pressure measuring device. So you know what is a pressure measuring device? You already did lab number 3, right? There is a tiny computer, and just you push the piston down and it shows a big pressure. You pull the piston this way and it shows a small pressure, right? In lab number 3. Have you got that? So there is a piston. So this is basically the tiny computer in our lab. They call the lab quest. So lab quest. So that's lab quest. So in our lab 3 or lab 3, we are using the lab quest. So here it is showing 1 atmosphere at this moment. 1 atmosphere, right? Now, so this is the same thing. Now push this really down. So here, so all the way down at a single step like this. So it all goes down here, and this 1 atmosphere now immediately shows about 5 atmosphere here. Maybe 5, 4, 6, 8. I don't know how many atmosphere we really pushing it down, right? In the single step. Everybody got that? Think about the lab number 3. So in one, using you put that piston at 5 and put a little bit off. That was about 8, and then put further 10, pull further 12, 15. You are pulling it up to 20, right? Just exactly like that. Now I am here, just pushing it down. At the beginning, this piston was here, and my lab quest was showing 1 atmosphere pressure. Now I really push it down like this, and my lab quest shows the 5 atmosphere pressure. Make sense? So what is the change in pressure here? dP. Change in pressure would be 5 minus 1 is 4 atmosphere. Everybody got that? Now I could do another way. So I have this like that, and I do this way. So again, so I push a little bit down from here. Let's say it was here. So I just push a little bit down here up to here. So now my lab quest here is showing 4 atmosphere. 4 atmosphere. You see that? I just push a little bit down at the 1 step, right? Now I can push a little bit further down here to here, and then now my lab quest shows me 5 atmosphere. So change is same, right? Previously I just push in single step and go from 1 atmosphere to 5 atmosphere. Now I am doing the same thing slowly in multiple steps, and I reach from 1 atmosphere to 5 atmosphere. Make sense? So what is the change in dP here? 5 minus 1 is again the 4. dP is 4 atmosphere. So no matter how fast, how many steps, how I walk, so the change in that property is same. Everybody got that? So the change in value does not depend how the process is done, whether it's done fast, whether it's done by heating, whether it's done by something else. So the change in that property is same. So we have change in volume, change in temperature, and change in pressure are state function. Yeah. So I write here a state function, a property whose value depends only on the initial state and the final state. Initial state was 1, final state is 5, 5 minus 1 is 4, right? But it does not depend how we did this process. Maybe I do single step, multiple step, 1 step, fast, slow, heating slowly, heating fast, it doesn't matter. Everybody got that? So it just depends on the initial, the change in that property just depend in the initial state and the final state. Got it? So like that. So the interesting thing is, let's talk about the not state function. So state function and non-state function. So non-state function in thermodynamics, those three terms are state function. And there is a work, W-O-R-K, work. This is a state, non-state function, work. That's you see that? So we are doing dq is equals to du plus p dv. So this is W, this is work. So this is work. So this is not state function. So it's a little bit hard to understand, but it's not a state function. Why it's non-state function is like this. So let's say you have this gas here, and let's say this goes from this is 1 liter and this is 5 liter here mark. So there are 2 mark, right? You can put many mark in the cylinder. Now you expand suddenly in 1 step. So maybe you are just putting this some kind of a screw here and just pull this screw out here, and there may be another set of screw. This piston suddenly shoot up and go and stop here. Make sense? Everybody got that what I'm saying? So there is a gas, and maybe this piston is movable, and something you put here, something here to hold on, and suddenly pull this, and maybe there is another set of screw here. You pull this 2 screw, and this gas just push this piston, and this gas goes, this piston goes here and reach here. Everybody got that? So it's a very fast, rapid expansion. So rapid expansion. So if that happens, rapid expansion, you will get very small work. So the work value, you will get small work value. Now, allow this to expand slowly. So from here, let this piston go here, and then from here, wait for a while, and then let this piston go here, and wait for a while, and then let this piston go here, and wait for a while. So if you do that way, and you get a lot of work. Make sense? So it's kind of, so you might have realized, or you might not have realized. So if you drive your car very fast, the fuel gives you more mile or less mile? Less mile, right? Exactly. So why less mile? Because you are doing rapid work. So if you're really doing fast, your fuel efficiency is very low. You didn't do a lot of work. Make sense? But if you are driving car slowly, you have 5 liter of fuel in you, maybe you can drive a month slowly, yeah? Slowly, a little bit. So that way your fuel efficiency is very high. Make sense? You are basically doing the same work, right? But the same phenomena. But if you do rapidly, if you drive your car rapidly, you did less work. So a lot of your fuel is wasted as a heat. Make sense? But if you drive your car slowly, with the same amount of fuel, you really drive long distance. Yeah. So that's the whole idea. So again, I don't want to tell a lot of story here. So basically, you have fuel here. Sorry, kind of fuel. So you have a gas here. So let's say this is 1 liter, 1 liter mark. So this is 1 liter mark. You are expanding this gas tiny bit. 1 step, 2 step, 3 step, 4 step, 5 step, 6 step, 7 step, 8 steps, tiny, to pull a little bit up, 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 in many steps. Yeah. So that's how we model thermodynamics. Yeah. Here we don't teach that one. So if you go to thermodynamics course in future, they will teach that one. So in many steps, 8 steps, I reach from 1 liter to 5 liter. So 1 liter to 5 liter mark here. So let's say the pressure, I don't know how much pressure is against that one. So basically dV, the volume change is 5 minus 1 is 4 liter, and I have many step pressure change there. So that's so how basically we will do is P1 dV plus P2 dV plus P3 dV. So it goes many steps, and we have to sum that. Got it? So work is basically not state function. If you do work slowly, you can do more work. If you do work fast, you do less work. Yeah. So it's just like if you walk slowly like this, you don't get that much fatigue. But if you just run at the same distance, you might get more fatigue, right? So it's different, right? So from here to, if I go from here to there, I walk slowly like this, slowly, and I don't get that much fatigue, right? But if I really run from here to there, I just burn a lot of calorie. Yeah, so I reach from here to there 2 way, and my fatigue is different, 1 way. I'm just tired. Another way, I didn't get tired, right? Or you can just walk up the hill from here to up there in your apartment. Yeah. So if you really run fast, you just get too tired. But if you walk slowly, you reach the same distance, but you didn't get tired, right? So that's not a state function. Make sense? Your initial state is here. Your final state is your apartment. If you really run fast, you got too much fatigue, too much tiredness. Yeah. So that's so initial state to final state. You are doing that, and you are too tired. But if you really go slowly from here to there, you don't get tiredness. Yeah. So tiredness is not a state function. Make sense? Tiredness is not state function. T-I-R-E-D. Tiredness is not state function. Not state function. Because so not in state function. Why? Because you go from here to that uphill apartment here. If you really go too fast, you get more tiredness. Tiredness. If you just walk slowly in many steps, but you are going from one state to another state, right? Your tiredness will be less tired there. So you are going from initial state to final state one way. You get tired too much. You are going from the initial state to final state in another way, meaning that moving fast, you get a lot of tired, right? So that is not a state function. So work is just like that. Yeah. Everyone got that? So work is like that. So if you expand the gas very fast, so if you expand, meaning that driving fast means expand the gas very fast. So if you expand the gas very fast, you get less work. If you expand the gas very slowly, you get more work. Yeah, more work means your fuel gives you more mileage. Yeah. Everyone got that? Yeah, probably you didn't get a lot, but at least you have some idea. So if I do the same thing, I get one value by doing the work, by doing the same thing two ways. Yeah. So that's a work is not a state function. So I write here a property whose value depends on path. Path means how you do the work. Yeah. Fast, slow, many step, or single step. Yeah. So if you do work slowly, you do more work. Yeah. If you do work more slowly, you do more work. So you are more efficient. Yeah. Your fuel efficiency is high. Yeah. If you do fast, you do less work. If you drive car fast, you lost more fuel because a lot of fuel is gone for the heat. Yeah. Not toward the work. If you drive car slowly, fuel lasts longer. So less fuel is needed. Yeah. So like that. Good. So already. So now let's talk another term here. Enthalpy. So there is another term called enthalpy. Enthalpy. So we give the again enthalpy is given by H, and again go to the first law of thermodynamics. The first law of thermodynamics is dq is equals to du plus pdv. Yeah, this is a piston movement by how much volume against some pressure. This is the change in internal energy. So basically change in temperature. So this is the heat absorbed by the gas, right? Now, if you are doing this work, this kind of thing in, let's say, something like this, open vessel, something like open vessel under the 1 atmosphere pressure. Yeah, open vessel. So if you do something like that, so that dq is called dh. So same thing, du plus pdv. So basically we are doing the reaction in an open vessel. Yeah. So if you so basically I don't know how much pressure is inside there because I am tightly putting this cap here. Have you got that? But if I put this cap open and I do something in here, I am doing the work under 1 atmosphere pressure because now this water is being pushed down by air 1 atmosphere pressure. Make sense? So if you are doing the things in the open vessel like this, so most of the reaction in chemistry laboratory we do in the open vessel. So in that case, that dq is called the th. Make sense? So if you are doing this, but if this is closed, maybe let's say you close here and you are doing this work and put you, let's say 5 kilogram weight here. Now you are doing something here. So that is Q here. You see that? Have you got that? Now you just remove this one and there is a kind of only 1 atmosphere pressure here. And in that condition, that dq and dh has the same meaning. So that dh is called enthalpy of the reaction. Make sense? But if you are putting like 5 kg or 10 kg of the weight here and measuring this dq, how much dv distance, that kind of thing, we cannot call enthalpy. We should call the heat. Make sense? Heat change. So if you are doing anything in the laboratory under 1 atmosphere pressure, that means most of the time we have open vessel to do the reaction. So in that case, if you measure the heat, that is called enthalpy. So in our laboratory, all the time we do the reaction in open vessel. Yeah. So under the 1 atmosphere pressure. So all the heat we measure, that dq is ds, basically enthalpy. Everybody got that? So enthalpy, basically this dq, probably they do in the very high level work, so changing a lot of weight here in the piston. But most of the reaction in the chemistry laboratory we do in the under the 1 atmosphere pressure. We just go to the lab and just put a beaker there. It's already open, and I have some water there, and I do some sodium hydroxide, and the beaker is open, and I just change the look at temperature change, and I use a Q is equal to mCT2 minus T1 equation, and whatever that Q I am measuring, basically I am measuring the enthalpy. Got it? So everything that we do in our chemistry lab is enthalpy. dq and dh have same meaning, but here in case of this one, I am doing the experiment in 1 atmospheric pressure. Basically 1 atmospheric pressure means I am not putting anything here in the piston. So basically that means that 1 atmosphere pressure, open vessel, so something like this. But here we might be doing the reaction or things under the very putting this piston on the piston, we might be putting a lot of weight here. If you got that, so basically dh is dq when we do the experiment in open vessel. Yeah, like open beaker. Good. Alrighty. So let's say I'm going to show you something that we will be doing in the next lab. So what we will do is we will do a big take a beaker here, and I put some water here. So let's say the mass of the water is m, and you already know the specific heat capacity of water is 4.12, right? And you put the thermometer here, and the temperature, the thermometer gives 21 degrees centigrade. Most of the time in our laboratory is about 21 degrees centigrade. And I throw some sodium hydroxide here, let's say 1 gram sodium hydroxide, I throw it here. And so sodium hydroxide react with the water, and the temperature just shoot up to, let's say, 30 degrees centigrade. So from 21, it shoot up to 30 degrees centigrade there. Make sense? So what I'm measuring here is basically Q. So dq is equals to m. So I even don't write Q now. mCT2 minus T1. So m is, I have how much m I have here? The sodium hydroxide, I put 1 gram. The mass of the water might be, let's say, 80 gram. So 80 gram in 1 gram, I might have 81 gram of the mass inside the that beaker. And C is I use the specific capacity of water, that is 4.18, and then T2, the temperature shoot to 30 degrees centigrade, and then initial temperature was 21 degrees centigrade. So whatever I am giving, getting number here by multiplication, this Q basically is the enthalpy. I'm measuring the enthalpy. Although it is a heat, we give this heat as a name as an enthalpy. Why? Because I'm doing the experiment, it is open beaker. If you got that? So if I do the experiment in open beaker, and if I measure the heat change, that Q is equal to mCT2 minus T1, basically here, although I'm measuring heat, I can call that heat as an enthalpy because I did that experiment in the open beaker. That's the only difference. Make sense? So if I have done this experiment under a very high pressure, so let's say I put a piston here, maybe I put a very, very large pressure here by putting something and measure the heat. In that case, I cannot call that as an enthalpy. That is Q in different conditions. Yeah. So that's the difference between Q and enthalpy. Everybody got that? So think that I'm doing the experiment is in open beaker, and I'm measuring the change in temperature from that reaction, and I apply Q is equal to mCT2 minus T1 equation, and I get a value of Q from that equation. That Q is enthalpy. Good. Alrighty. So thermodynamics is a lot confusing due to this different kind of terms, and they use in different conditions. So like that. So now I'm in slide number 4. So let's look here. I have water here. So basically I have 18-gram water. So this is my beaker here. This is my beaker, and I have 18-gram water. Why 18 gram? I have 18-gram water, 1 mole of water. So H2O is H is 1, another H is 1, 2, oxygen is 16. So 16 plus 2 is 18. So molar mass of water is 18 gram. Everybody got that? You already know about this mole thing, right? You already did one exam and you all did good. So I think so. I put 18 gram of water, and I want to put. I want to break all this 18-gram water, 18-gram water in the gaseous state to hydrogen and oxygen. So like that. So if I want to break all 18-gram water here into hydrogen and oxygen, I need to supply how much energy from outside is 241. 41.8 kilojoule. 241.8 kilojoule. So I put this in heater here, and I keep heating. So I just blocking this by putting something there, a non-explodable thing. Yeah. So I keep heating, keep heating. When I put this one 241.8 kilojoule heat from here to here, all this water breaks into hydrogen and oxygen. Make sense? So that means that. So basically, so what I'm writing here is, so this one, and they're just balancing like this one, and they're writing plus a half, sorry. So delta H is equals to 2 plus 241.8 kilojoule per mole, meaning that you need to take 1 mole of water, which is 18 gram. So if you want to break 18 gram of water into hydrogen and oxygen, you must supply 241 kilojoule of heat energy from outside, so that all that 18-gram water breaks to hydrogen and oxygen. Everybody got that? So good. So that is called enthalpy change during the so enthalpy change for molar enthalpy change. Why? Because I'm taking 1 mole of water, 18 gram molar enthalpy change. Yeah. Good. You need to take 1 mole of the material and do the reaction. Yeah, molar enthalpy. So another one is, let's do. So this is a little bit harder process. So we cannot basically heat the water and break the water that easily. We don't have the infrastructure in the laboratory. We need to supply some electricity and do the electrolysis of water by heating. To break the water vapor by heating is a hard process. Yeah. So the easy process to understand this is another way. So let's put here H2 plus O2 gives what happens if you bond it. So mix, take some hydrogen here and oxygen here and fire it with a matchstick or something, and you get the water here. So the reaction is like this. So it will give minus 241.8 kilojoule per mole of water, So look here. So here you are making 1 mole of water, meaning that you are making 18 gram of water. If you got that, 1 mole water means 18 gram water. If you want to make 18 gram water from by mixing oxygen and hydrogen, to make that, while making 18 gram water from hydrogen and oxygen, you get this much heat out. So when you burn hydrogen with oxygen, it gives a lot of heat out. Yeah. So how much heat it gives out? So this minus is, we are getting heat out of the thing. So the vessel is becoming hot, like the car engine. Make sense? When you burn the fuel in car engine become hot, right? So that means minus. We are becoming hot here. So basically we are getting a lot of energy out. So how much water I am making here? 18 gram. So if I am mixing hydrogen and oxygen and making 18 gram of water, I am also getting in that process minus 241.8 kilojoule heat energy. If you got that, so that means that. Good. Good. So now let's do some problem here, and so I'm in the slide number 5. It says the standard molar enthalpy. Molar enthalpy means 1 mole. You are burning 1 mole. Yeah. So standard molar enthalpy of this one, C3H8. H8, it's a gas, and you are burning it with oxygen. So that's propane. You are burning with oxygen, and you are getting carbon dioxide and water. Again, this you don't have to balance yourself. It's already balanced. So balance is here is 5. Here is 3, and here is 4. So the standard molar enthalpy of the propane is, so what is molar enthalpy? So if you want 1 mole of propane, so 1 mole means, so look here, 1 mole means how much? So 3C. So 1 carbon is 12, right? Yeah, 1 carbon is 12. 12 multiplied by 3 is 36. 1 hydrogen is 1. I have 8 there. So 6, 8, 14. 3, 1, 4. So if you want 44 gram of propane, they are saying you would get 2044 heat out. You feel hot. Make sense? They're burning the, so the here minus sign here means the room becoming hot here. If you got that, so if the room becomes cold, that's a plus. If the room becomes hot, that's minus. Make sense? So if you want 44 gram of the propane, you get how much? Minus 2044. Minus 2044. Again, this minus sign is not negative. It is coming out. Yeah, it is coming out. We are feeling hot. Yeah. So kilojoule per mole. Per mole means what? 1 mole. Right? If you want 1 mole of this propane, you get that much heat. That's what it is saying, right? Everybody got that? So if you want 1 mole, 1 mole means 44 gram of propane, you get that much heat out. And the question is, what is the standard enthalpy change for the combustion of 3 mole? So 1 mole value is already given. You now need to know how much is the heat given by if you want 3 mole of propane. So 1 mole gives this much. 3 mole, if you want 3 mole of the propane, how much heat you would get? So you just put there 3 times, right? See, if you want 1 mole, you get that much. If you want 3 mole, how much you got? So you just take the ratio here and calculate the value of X here, just like that. So if you just directly know, oh, I need to multiply here, you even don't have to take this ratio like this way. Yeah. So look here, 1 mole gives 22,000. 3 mole would give 6,000. Isn't that easy? Right? So if you work 1 hour, you earn 2,000. If you work 3 hours, you should earn 6,000, right? Easy. Everybody got that? So by burning 1 mole, you get 2044. By burning 3 mole, how much you would get? So you just cancel this one here and take that guy this way. So 2044 here, and then you get approximately 6,000. So put this number in calculator. Mole is gone. So this is kilojoule. Kilojoule goes there. So that is X is equals to 3 multiplied by 2044 is 616132, and minus sign is there. So minus, what does that minus sign tells us? Basically, I'm burning the propane here and I'm feeling hot here. Yeah, heat is coming out from that. Everybody got that? You even don't have to do this way. If 1 mole gives this much, 3 mole would give 3 times of that much, right? Got it? Easy. So if I work 1 hour, I make $20. If I work 3 hours, I make $6, right? $2, $6, right? Simple. So another one here. Let's look another one. Molar enthalpy of the combustion of ethanol. So combustion of molar enthalpy is already given 1 mole. So if you burn 1 mole of ethanol, 1 mole would give how much heat? Simple alcohol having formula C2H5 is giving minus 277.7 kilojoule. Saying the kilojoule per mole. They are writing the per mole here. Basically, if you burn 1 mole, you get that much heat. So I'm just writing the same thing this way. If you burn 1 mole of ethanol, you get that much heat, right? Make sense? Easy. So 1 mole of ethanol means you have a C2H5OH. So C2H5OH is a ethanol. So how much you are burning there? So carbon is 2. So 12 multiplied by 2 is 24. Hydrogen is 5. Oxygen is 16. Hydrogen is 1. So you add this. When you add those, so there will be 4, 5, 9, 6, 15, 16, 2, 3, 4. So if you want 46 gram of ethanol, you would get that much heat. That means that. Everybody got that? Make sense? And then it is asking what quantity energy as heat will be released by the combustion of 9.22 gram of liquid. Look here. So this is in mole. He's asking in a gram now. Now that gram I need to convert into mole, right? Everybody got that? So the value is given. 1 mole gives that much. He's asking 9.22 gram would give how many kilojoule here? Here is a mole, here is a gram. So I cannot work in that way. Yeah. If I mole here, I need to be mole here too, right? So 9.22 would be. So I change that 9.22 into mole. 9.22 a gram. So in converting into mole is 46. 1 gram, 1 mole up there, 46 gram down here. So you just cancel gram. 9.22 by 46 will give you 0.200. 0.200. So this number is 0.200. 200 moles of ethanol. How many mole of heat you would get? So just like that. Or you could write this in the up here for easy. So I put 0.200 and I put that x up here. So the math becomes much easier if you put the x toward up than down. Yeah. Otherwise it takes long time to calculate. So directly you take the ratio. Now x divided by minus 277.7 is equals to that 0.200 divided by 1 mole. So this guy go there and multiply and you get how much? 55. So this multiply by this. So x is equals to 0.200 multiplied by minus 277.7 and it gives you 55.55 kilojoule. So if it, so that's a kilojoule, it comes in the kilojoule, 55.5 kilojoule. So what does that minus mean? That minus means I'm burning the things there and I'm getting a lot of heat out. I'm feeling hot. Makes sense? That means the exothermic reaction. Minus means if I burn something that gives hot to make the room very hot. Yeah. Have you got that? So if that is in mole, you must convert gram to mole. That's all. Otherwise, just taking the ratio. So I write already there is a 1 mole of ethanol is 46 gram. So now molar enthalpy of octane vapor is that much. How many grams must be burned? So again, in the 7th slide, so let's do this problem here. So molar enthalpy of octane is given. So molar enthalpy of octane means the 1 mole octane is they are burning and they are getting how much heat? 5451 kilojoule per mole. They are writing the 5451 kilojoule per mole. That is same as 1 mole giving that much heat. And this is minus. So if you burn octane, it gives heat out. That's minus means. Yeah. Everybody got that? So like that. And so in this problem, the behind that reaction, they are writing plus 5451. That's not plus. That's really minus. Yeah. So if you look at that slide number 7, the C8, 18, 12, half O2, whatever they are doing, and they are writing plus 5451. That's not plus. That's minus. Yeah. Good. So that's minus. So that's minus that much. And how many grams must be burned to obtain 105 kilojoules? So they are giving how many? If I burn 1 mole, I get that much heat. So if I burn how many mole, I would get 105 kilojoules. So that's the problem. So 105 kilojoules. Yeah, right? Make sense? So how many mole I should burn? So I write x here. Make sense? So just take the ratio. X divided by 1 is equals to minus 105 divided by minus 5451 kilojoule, and then you can cancel minus and minus, doesn't matter. X is equals to how much? This gives you I don't know how many moles it gives. So let's say 105 divided by 5. So I have not written here, so I'm going to write it. So both are minus. Yeah, if you didn't see minus before those number, that should be minus. Everyone got that? So this is 105 divided by 5451. So that is 0.019 kilojoule, 0.019 kilojoule. So that many mole, I need to want that many mole to get that much heat. You see that? Now 0. Mole. So now they're asking, because how much mole, how many gram we should, because we don't have the balance to measure the mole, right? So I cannot measure 0.019 mole in the laboratory. I need to measure that in grams. So convert that into gram, right? So octane is the molar mass of octane is, I don't know, molar mass of octane. So if it is not given, you can write here. So octane is C8H18, H18. So 1 C is 12, 12 multiplied by 8 is 96. I have 1 H is 1, 18 H is 18, right? That's how we calculate the molar mass, right? So this is 8 and 6 is 14, 1, 10, 11, 114. So 114 gram, 1 mole is equals to 114 gram. Got it? Hopefully I did the right thing. C8H18 is molar mass is 114 gram. Or you can just go to the Google and put the molar mass of octane in Google, and Google will give you the molar mass. Make sense? Good. So this is the number of mole of the octane I need to measure. So, but I cannot measure the number of moles in laboratory. So I need to convert this into a gram. So 0.019 moles. So I put that factor in such a way that I want a gram. So I put 114 gram up there and 1 mole down there. So 114 multiplied by 0.09 give you 2.20 gram, something like that. Everybody got that? Reason if you get a minus sign while doing a mass calculation, especially calculation, don't worry about that. You just disregard that minus sign. Yeah. Good. All right. So sometimes small thing gives a lot of trouble. Oh, I'm getting minus mass. So what's going on here? So basically, somewhere you need to put that minus. You forgot to put that minus, and minus did not cancel, so which is fine. Yeah. If you get the number mass cannot be negative, and that is. So I always was confused with the thermodynamics. So once I taught this course in UW Milwaukee for engineering student, and then I fully understood this. This is very confusing. Yeah, somewhere minus, somewhere plus, somewhere work plus, somewhere U plus. What's going? It's very confusing if you go to add the book and start to write the book yourself. Yeah. So like that. So now, so those things are important, but rather than this is important, what I'm going to talk is more important. Yeah. So this is called coffee cup calorimeter. Coffee cup calorimeter, and we will be doing this in laboratory. Coffee cup calorimeter. So you already know what is coffee cup. So you go to the Dunkin' Donut or Quick Trip, and you have a coffee cup there, right? So what we do here is you take 2 coffee cups. So take 2 cups. This is 1 coffee cup, and take another coffee cup. So 2 styrofoam. Basically, they are made up of styrofoam. 2 coffee cups here, like that. And let's put 10 gram of water here. So go to the balance and measure 10 gram of water in the car and throw it here. So you put 10 gram of water, 10 gram water. Everybody got that? Coffee cup. Yeah, this is nothing. It's just a coffee cup that comes in maybe 25 cents in Dunkin' Donut. Yeah. So I put 2 coffee cups. Why I put 2 coffee cups? I just want to make this thing very insulated, so that if there is a heat inside, heat doesn't go outside. If there is a hot outside, or hot outside, heat cannot come inside. Therefore, I put 2 coffee cups there. Yeah, make sense? Insulated. So basically, it's like in the cold day, you put many layers of clothes, so that outside cold cannot touch you. Yeah. So like that. And so 2 coffee cups. Now put a thermometer. So what does the thermometer do? It measures the temperature, right? Make sense? And in the coffee cup, there is a tiny hole to drink the coffee. So it has a cap, right? So cap. So you have a cap, like this, and from that, there is a tiny hole, so you can put the thermometer like that way. Everybody got that? Easy. So take the 2 coffee cup, put one over another, and from the cap it with the cap of the coffee cup. Maybe you are drinking now, and there is a hole. From that hole, just to put the thermometer there and record the temperature. So maybe this is water. So maybe the temperature now is 21 degrees centigrade. Most of the time, our laboratory water is 21 degrees centigrade. You already know from lab 1 or lab number another, right? So 21 degrees centigrade. Make sense? Good. Now, how much water I put here? Oh, 10 gram, not, yes, 10 gram, right? Yeah, 10 gram water. So 10 gram water I put here. I put the thermometer, I put the cap, and I put the cap there now, and measure the temperature here. I'm writing 25 degrees centigrade, so I'm going to write 25 degrees centigrade here. Yeah. So we will be doing in the laboratory. Now, throw 2 grams sodium iodide. Open it. So open it quickly and throw 2 gram of NaOH. 2 gram of NaOH here immediately, and close this. Why immediately close? If you don't close immediately, the heat is generated here from the reaction, and that heat is go outside. So immediately you need to close the cap to prevent that heat here. Make sense? Everybody got that? So this experiment cannot be done in the iron plate, iron open vessel, or a copper vessel or something, because they are the good conductor of the heat. Heat just escape from outside to inside, inside to outside, like that. So we need a very insulator kind of thing, like a coffee cup calorimeter, which can make the thing hot long time, like thermoflask. Everybody got that? So immediately I close this one and just shake it a little bit. When shake it, all sodium hydroxide react with the water, and this becomes very hot, and temperature from 25 degrees centigrade shoot up to 40 degrees centigrade. Everybody got that? That's it. So this is the experiment we are going to laboratory, and this is the very fundamental work in thermodynamics. Now, how many dollars it costs to do this experiment? $2, $3, $5, right? But nowadays, people from this one, they make the very expensive calorimeter. They can sell in $50,000 or $1 million. So they make the very expensive calorimeter just to do this work. Make sense? So now let's see how much heat is generated here. So heat generation is, so basically Q is equals to how much heat is generated by reaction of the 2 gram sodium hydroxide with 10 gram water. Q is equals to MC T2 minus T1. Always thermodynamics doesn't have other equation. This is this only equation we have. This is one equation, and another equation is dQ is equals to du plus PdV. Yeah, so thermodynamics is only 2 equations, and we just modify those equations for our purpose. Look here, how much heat is generated. So it becomes hot. So how much heat is released? So M is, you have 10 gram water, 2 gram NaOH. You have 12 gram mass there. Make sense? 12 gram. And what is the specific capacity of water? So the specific capacity of water is 4.18, and T2 is 40 degree, and initial you had 25 degree. 40 minus 25. So now put this number in calculator, and you get 752.4 joule of heat energy. Look here. It's very hard to measure the heat. There is no other way to measure the heat. Only we just look the temperature change and use that temperature change, mass, and specific capacity of something, and we can calculate how much heat is being evolved, how much heat energy is going out. You see that? Heat cannot be measured directly, so we need to take help of temperature. So there is no other way of measuring heat. Yeah? Very important. Temperature, just buy a $2 thermometer, just put that there, and you can easily measure the temperature, right? But you heat every day, you in the kitchen, every day you heat water. You don't know how much heat you are using to heat your water, right? Because there is no way to measure the heat. Yeah, so you must take the thermometer and take the initial temperature, take the final temperature after being hot, and how much is the mass. You need to take that mass, and you need to know C is equals to 4.18 and Q is equal to MCT2 minus T1. So that's the only way in the universe to measure the heat. There is no easy way. Everybody got that? Very important. Temperature is very easy to measure. Heat cannot be measured, right? We need to take help of this equation. Got it? So everybody, you got one question from in the coffee cup calorimeter, and there are some questions from in homework, and we will be doing in the laboratory also. So it's very important, yeah, because if coffee cup calorimeter people did not invent it, I don't think anybody would be doing any heat calculation these days. Yeah, there is no other way. Yeah, good. So that from that simple thing, just go home and Google expensive calorimeter. Calorimeter means measuring heat. Calorie means heat. Meter means measurement. So it's a device to measure the calorie. Yeah. So all the things are done this way. And if you look in the Google, oh, expensive calorimeter is 50,000, 60,000, $1 million. So they are selling that expensive this equipment. Yeah. So maybe in future you will work in those things. And so I'm going to. All right, we still have 20 minutes time. Now, so coffee cup calorimeter is done. Now let's do one problem here. So one problem here is a coffee cup calorimeter. He's saying and 6.50 gram of sodium hydroxide. So here is water, and the water is 100 gram water here. So water is 100 gram, and he's throwing the sodium hydroxide here. That is 6.50 gram, and before throwing the sodium hydroxide here, he measured the temperature here. The temperature was 21.6 degrees centigrade. Then he threw the 6.5 gram of sodium hydroxide here. And then immediately cap it, and he shake a little bit, and after shaking, the temperature shoot up to give 37.8 degrees centigrade, right? And it is asking us what to find here. So basically heat. So let me calculate the delta H, meaning that find the heat. Make sense? Same thing. So heat is again Q is equals to mCT2 minus T1. Like that. M is, so this is 100, this is 6.5. So 100 6.5 is the mass, and C of the water. So we don't consider the specific capacity of that NaOH much difference than water. So that is 4.18, and T2 is 37.8 minus 21.6, and you get a number. That number comes to be 7212 joules, like this. So if you divide this number by 1,000, you get kilojoule, 7.212 kilojoule. That much heat is produced by mixing 6.50 gram of NaOH in 100 gram of water. Make sense? If you got that, pretty simple, right? Just take some water in coffee cup calorimeter, 100 gram, measure the temperature, that is 21.6 degrees centigrade. Then throw 6.50 gram of sodium hydroxide there, immediately cap the cup, and then shake it, and the temperature shoots up to 37.8 degrees centigrade. We apply this one, and since we are doing this in open vessel, so there is an open vessel here, we are not pushing it, so that Q is basically enthalpy. Yeah. So there is no difference in our chemistry between Q and H. Everyone got that? Same thing. So that's the enthalpy. So from how much you get that heat? From 6.50 gram. If you use 6.50 gram of NaOH, you would get that much heat, right? Now, so how many mole? So convert this one into mole. So they are asking how many, if instead of 6.50 gram NaOH, what is the molar mass of NaOH? Na is 23, O is 16, H is 1, 40. So instead of 6.50 gram, if you have thrown 40 gram here, how much heat it would produce? That's what they are asking. Make sense? Good. So either way is fine. So let's say you can do like this way also. So instead of 6.50, so you have 100. How much is that one? 6.50 gram. So 6.50 gram NaOH. If you have thrown 6.50 gram NaOH, you would get how much heat? That much, 7.212. So instead of 6.50, if you have used a 40 gram is this one, right? 1 mole. how much heat you would get. So x divided by 7.212 is equals to 40 divided by 6.50. You just take this way there, 40 multiplied by 7 divided by 6.5, and you would get 44.3 or something like that. Everyone got that? But instead of doing that, you could also convert this 6.50 gram to mole. Yeah. So 6.50 gram, if you convert that into mole, that is 0.1625 moles. And then here you write 0.1625 moles. That is gives that much heat. And then 40 gram would be 1 mole, and that 1 mole would give that much. So in this one, I did that way. You got that? So this one, 6.50 gram is how many mole? You have to multiply 1 mole divided by 40 gram, right? Because 1 mole of NaOH is 1 mole of NaOH. 1 mole of NaOH is equals to 40 gram. So you need to convert this gram to mole. So 1 mole divided by 40 gram. So when you divide this by this 40 gram, you get 0.1625. So 6.50 gram basically is that many mole. So that many mole gives that much heat. So they are asking how much heat we produce if I want 1 mole, right? That's x mole. So x kilojoules. So x divided by that 7.212 is equals to 1 divided by 0.1625. So whether you want to do it gram to gram or mole to mole, it's the same. Yeah, it gives the same answer. Everybody got that? So rather than doing this, I could do 40 gram here, 6.50 gram here, and x 7 point this one, and I would get the same answer. Yeah. A little bit confusing because of this unit conversion. Yeah. Good. Yeah, but most of the time I just use the asked in introductory course. I just ask just to use the Q is equal to mCT2 minus T1 rather than going further to the mole, to gram, to mole. Yeah. Everybody got that? So coffee cup calorimeter is really important. So when I was a student, I didn't realize that this is that important. Yeah. So I only know it's important after I started teaching. Yeah. So already, so you can do that and try those things. We have some 10-minute time here. So now I'm going to talk another concept, but this concept is we will be using, but it's not as important as coffee cup calorimeter. Yeah. So it's a Hess's law. So this is a here is a law. Where is that? Oh, Hess law. So I am in the slide number 10 today. So Hess's law. Hess's law. So Hess law is basically is a state function. So state function means you can go step 1 step, 2 step, 3 step, 4 step, 5 step, and you or you can directly fly from here to there. Yeah. So the change is same. State function. Make sense? So step, for example, let's say you have a 10 step here. So this is a ladder here. So let's say 1, 2, 3, 4, 5. So you want to reach here. So 1 step, 2, 3, 4, 5, 6 steps. So you in 6 steps you reach here. Make sense? You just walk 6 steps, right? Somebody might say, oh, I don't want to walk 6 steps. I just want to take a helicopter here and I want to fly. Yeah. So you could fly from here, taking a tiny toy helicopter, and then you reach here like that. So from here you reach the same thing. So the change is same. Either you take the helicopter or you just go many steps or you just run in 1 step. It doesn't matter. Whichever way you do, you get the same value in change of that property. Everyone got that? So here we are talking about heat. So let's write down. So let's say you have one chemical A, and you did some heating here and directly changed to E. 1 step. Make sense? So you have a chemical A like calcium carbonate, and you heat it very high temperature, and it immediately break into calcium oxide and carbon dioxide. Make sense? Like that. Make sense? 1 step. Immediately put in the beaker, heat it, and in 1 step it break, right? So another way you could say, all right, so you could say like this. Oh, I have a A. Now I want to convert A to B, and from B I want to convert to another chemical C, and from C I want to convert to the D, and I want to heat that D and convert to E. So you are just going from A to E in two ways. Make sense? Got it? So let's say from here, going from here to here, you measure you apply the Q is equal to MC T2 minus T1 equation and found that that heat is delta S. Maybe that is 100 joule, 1000 joule, 1 kilojoule. I don't know how much joule you got, right? So again, the equation is to calculate that delta S, you have to throw everything in coffee cup calorimeter, initial temperature, final temperature, mass, MC T2 minus T1 you do, and calculate the number, and you get one number here. Make sense? Just convert A to E. Now another way, all right, so you converted A to B, so maybe and calculated the heat, this is delta H1. So B to C, and you measure the heat, delta H2. Just doing coffee cup calorimeter, yeah? There is no other way to do it, yeah? So another, and then C you change to D, and the heat change was delta S3. And from D you change to E, and you got delta S4 heat. Now you sum this one, this one, this one, this one, and that sum becomes equal to this direct state. Yeah, no matter which path you follow, you get the same amount of heat change or enthalpy change or Q, whatever you want to. Everyone got that? So here delta H means Q, yeah, MCT2 minus T1. Why they are writing delta H here? Because they are doing the reaction in open vessel. Yeah. So delta is nothing other than Q here. Delta. How to calculate delta H? Delta H is MC T2 minus T1. So this is basically Q because we are doing this reaction in open vessel. Yeah. So the delta H, so this heat would be equal to delta H1 plus delta H2 plus delta H3 plus delta H4, like that. Got it? Make sense? So somebody just come to class and just by studying in the class pass, right? So they are just jump from one state to another state, right? Somebody might go from class and I'm not confident. So they might go to the tutor and then again, tutor is not, so I might go to online to learning and many steps and they still pass, right? So no matter, you just directly go from here to here or go from this way to here, you are just passing the same state. Make sense? Just like, so let's say going from here to here is 1000 joule here, 1000 joule here. So maybe this is 200 joule, this is 300 joule, this is 400 joule, and maybe this one is 100 joule. Now look here, 200, 500, for 900, 100, 1000. And this way is also 1000 joule, right? Make sense? No matter which way you do the calculation, the total, this is one part, it gives the same amount of heat as the direct path. Or only or other kind of path. How many paths are there? Yeah. So no matter how many steps you do, the net sum of the heat is same. If you got that? Okay, like that. So already, so like that. Now so I'm almost done. Now here is one example here for the Hess's law here. So let's do this example here. Here is this is a methane gas, and we are burning with oxygen, giving carbon dioxide and water. And this process we did in coffee cup calorimeter. Basically, I take coffee cup calorimeter here, and then put CS4 here, and then put oxygen here, and put the thermometer, measure initial temperature, measure total mass, and then I burn it, fire it a little bit using a fire, and then measure the final temperature, and I use a Q is equal to MCT2 minus T1, and I get the value minus 890 kilojoule, minus 890 kilojoule per mole. Make sense? So we got that just by doing the coffee cup calorimeter. Although we cannot use the coffee cup calorimeter. If you burn things in coffee cup calorimeter, you are going to burn the calorimeter, right? So similar to that. So there are other kind of the material which is exactly like the coffee cup calorimeter. Make sense? Can you burn something in coffee cup calorimeter? Definitely not. Coffee cup calorimeter is styrofoam, and you just melt it, right, with the fire. So, but The concept is we are just doing the process of calorimeter kind of thing. Good. Now, this is one step, and that much heat is coming out from the reaction. But you could do another way also. So this is one way. This is direct way of converting methane and oxygen to carbon dioxide oxide in water. But in part B, you could be doing this one. CS4, 2O2, and then you could make carbon monoxide and water and half oxygen like that in one step. And then you measure the heat, and that comes to be minus 607 kilojoule. And then now you go from A to B. Here you are going from A to direct to C. Here you are going from A to B first. And now from there you need to go to CO plus 2H2O plus half O2, and then you can go to CO2 plus 2H2O. Look here. Now you reach to here. This is A. You directly reach to C. But in this way, you go from A. So this is A. You go to B, and from B you go to C. You see that? Here you are doing the same thing in two steps. There you just did directly in the single step. Make sense? You got it? Same thing. Look at A. This is A thing directly change to C thing. But when you take the A thing here, you convert it to B things, and then the B, you take the B things and then convert to the C thing. So this guy and this guy is same, like that. So what is the now? How many heat we have? I have 607 here. I have 607 here. How much heat I would have here? So I don't know. That's an X heat. I say I don't know how much heat they are giving here. They are not giving anything. So from this step, I measure this one, but this step I don't know. Now I can use the Hess's law. So this plus this is a multiple step. This is single step. So this plus this must be equal to this, right? Make sense? These are two steps. So I'm doing the same. This is one step. This is two steps. So this sum of these two steps must be equal to that direct step, right? So minus x plus 600. So just take the minus 607. So basically I'm adding this one and this one, and that number must be equals to minus 890, like that. See that? This is a single step. So I'm just getting two hits there, right? Got it? So now let's calculate that one, and that comes to be, so basically 607 and minus 283. So that's minus 890. So x minus x is equals to minus 890 plus 607. So that gives me how much? So this is minus 890, basically kilojoule. So that sorry for that. So that's equals to how much? So that is 283 minus 283 minus 283. So that minus x is 283. Look at, so if you put minus 283 here, minus 283, minus 607. So if you add this one and this one, that gives you that number, right? Got it? All right, so that's how we do. Yeah, but this Hess law, we will do some this kind of equation in lab also. So basically, this is A to C directly. Here A to B and B converting to C, and I have A converting to B and B converting to C. Two heat here. So this heat plus this heat must be equal to this heat. So if I don't do that heat, I can calculate that heat, right? Everyone got that? Good. So I have just 2 slides. I will complete in next class, and we start the 6th chapter. Yeah. So, all right, everyone. Thank you very much. Somebody says something here. Let's see. Who is playing? All right. Thank you, everyone. So I'm going to end this one. Who can see your messages recording? All right.